Hello everyone, I hope you're all doing great. Today's video is going to be looking at drawing and naming alkenes and having a kind of a further look into more complicated structures of alkenes when we've got branches, a little bit like we did last time or a couple of episodes ago with alkanes. So we're going to have a more in-depth look at these alkenes today, and there's a couple of little additional pieces of information that we need to bear in mind when we're drawing or naming structures like alkenes when there's a double bond involved, because it changes what we do ever so slightly, and that double bond is very important, which we'll see in great detail today. And just like with when we were talking about naming and drawing alkanes, with the alkenes we need to be able to name and draw up to oct, up to structures that contain a straight chain of 8 carbons. Don't need to go any higher than that, but 8 is where we need to be comfortable with. So all the way from eth up to oct for our alkenes. Now if we remember correctly, our alkenes are our second homologous series that we looked at, and they contain a kind of special bond called the carbon to carbon double bond. So we need to remember that these alkenes contain double bonds, and they have the general formula CnH2n. Help if I put the H in. Apologies. CnH2n. Now then, if we look at the first member of this homologous series, we've looked at this before, but it's worth just remembering some of the key things. Here is ethene. There's the first member of our alkenes. Eth because it's got 2 carbons in its straight chain, and it has a carbon to carbon double bond. It follows a general formula CnH2n, so it must be ethene, and that's very straightforward and very simple. What we're going to come and what you're going to come to see quite commonly put into the names of alkenes are numbers. And so you wouldn't get a number in this example, I'll explain why in a second, but let's say we took a different alkene. Let's say we had butene and they represented it like this. But1ene. Now that's very important, and it's very important that we put a 1 into the correct butene structure, because in actual fact there is more than one different type of butene. If you just write down butene, it's not specific enough. It's not specific enough because the carbon-to-carbon double bond within the butene molecule can have different positions. So I'll show you what I mean now. Let's say we were looking at this one we've already drawn out, but1ene. We know there's going to be 4 carbons because that's what the but stands for, so we'll draw out 4 carbons. And I have a little look at the last 3 letters. It's ene. Right, I know it's going to be an alkene, I know it's going to contain a double bond, but I've got a decision to make. If I was just looking at this name here, where there's no number, I have no idea where this carbon-to-carbon double bond goes. Does it go here, between the first 2 carbons? Does it go here, between the second and third carbon? Don't know. So that's why that number within the butene is very important. That tells me that it's going to go on carbon number 1, or at least the double bond will start at carbon number 1. Here's carbon number 1, and there's where I'm putting on the carbon to carbon double bond. Then I know the rest of them are single bonds, and I can put in the hydrogens accordingly. This carbon's already got 2 bonds, so it needs another 2 to make 4. This second carbon has 1, 2, 3 bonds, so it just needs 1 more. This one has 2, so it needs another 2. And the last one only has 1, so it needs another 3. And there is but1ene. Now we could also have but2ene, and that would be going through the exact same setup, drawing our 4 carbons because it says but. Ene means there's a double bond, and the 2 in front of the ene tells me that this time it's not between carbon number 1 and carbon number 2, it is between carbon 2 and 3, or a more simpler way to think about it is the double bond starts at carbon number 2. That's what that number 2 means. Here's a double bond, there's carbon number 2, there's 1, there's 2, so the double bond must be on carbon number 2. And then put in the rest of the bonds, making it a complete molecule, making sure every carbon has 4 bonds. This is where it gets not tricky at all, but where people make silly mistakes. They just go like this and throw in hydrogens everywhere, and you'll soon see that that is definitely not correct for a number of reasons. If I just put in hydrogens everywhere, this molecule, we know it's an alkene, it must have the general formula CnH2n. If I count up the number of hydrogens, I count up the number of carbons, I don't have an alkene. I've got far too many hydrogens. And if I look at these 2 carbons in the middle here, they've got 1, 2, 3, 4, 5 bonds. 1, 2, 3, 4, 5 bonds. So you can't just go in and throw in hydrogens wherever you please. You really need to think about where they should go and why, and making sure every carbon has 4 bonds. Right, let's look at one more example of that just to make sure we are crystal clear with what we mean by this number and what we mean with the double bond. So let's draw this. Let's do another butene. This time I'll put the carbon-carbon double bond all the way over on the right hand side. Putting in my hydrogens, as we've talked about, making sure every carbon has 4 bonds and 4 bonds only. This one already had 3, so it just needs 1 more. This one already had 2, so it just needs 1 more. So let's say we were given this structure here. We were given this structure here and we were asked to name it. Well, if we go through our normal steps, we go 1, 2, 3, 4 carbons is in the longest chain. It must be bute. I'm going to leave a little gap for the number. Have a little look at the types of bonds we've got. We've got carbon-to-carbon double bond. It's represented by CnH2n. Must be an alkene, so it's going to end in ENE. I've left that gap so I can put in the correct number. And what do you think we should go for here? Should it be bute 3ene? Is that correct? It isn't correct. This is not bute 3ene. Even though it looks like it, this is actually just bute 1ene. You might be sat there confused, so pay attention, because remember our numbering systems can go either from left to right or right to left, and we must always make sure that something like a carbon-to-carbon double bond has the smallest possible number. So this is definitely bute 1ene, it is definitely not bute 3ene, and here's why. If we were to number from left to right, and say this is carbon number 1, 2, 3, 4, then yes, this double bond is on carbon number 3, starting at carbon number 3, so you'd be expecting it to be bute 3ene. But we've already said that that's wrong. Why is it wrong? Because we could quite simply just number it from the opposite direction, going from right to left. And if we number it from right to left, the double bond starts at carbon number 1. So this is in fact bute 1ene. And there's no such thing. Bute 3ene does not exist. That is not a viable compound. It doesn't exist because it is just simply bute 1ene. Remember, these molecules can be kind of rotated and flipped. It's very hard for me to show it on this piece of paper because I can't pick it up and flip it. But if you could pick it up, reach your hand into the screen, pick up those carbons and hydrogens, you could rotate it round in 3D. And that is what these molecules can do. So this is bute 1ene. Again, there's no such thing as bute 3ene. Now let's take that piece of information, what we've just learned about the numbering and positioning of a carbon-to-carbon double bond, and take it in to some more complicated examples now where we have branches. We've already looked at examples like this when we looked at alkanes, where we first found the longest chain, then we numbered the chain, identified the branches, and then numbered the branches. The steps are all pretty much the exact same. However, there's a slight difference when naming branch-chained alkenes because of that double bond. Now that double bond, that carbon-to-carbon double bond, is the most important thing within these structures. It's even more important than the branches. So when we come to number the chain, we must use the carbon to carbon double bond as our kind of anchor point, as what we make sure we are numbering the chain in order to give the double bond the smallest possible number. And once we've done that, when we've got our numbering system, we can go on to the branches. We'll have a little look at some examples now, and trust me, within about 2 or 3 it'll click, you'll get it, and you'll be ready to do some naming and drawing by yourself. Right then, let's apply these steps and try and name this structure that I have got on the right hand side of the screen. Let's quickly go through the steps again. Number 1, find the longest chain of carbon atoms. Longest chain of carbon atoms. Now I've also written something there as well. Also contains. This is very important. Also contains what? Well, when we're looking at identifying and drawing and naming an alkene, as we've said, that carbon to carbon double bond is very important. So step 1, slight alteration. We're not just finding the longest chain anymore. We must find the longest chain that also contains a carbon to carbon double bond. That will make sense in this example in just a second. Then we number the chain using the carbon to carbon double bond. We'll identify any branches, number the branches, and then write down the name. So, first step, find the longest chain of carbon atoms that contains this carbon to carbon double bond. So, a couple of choices here. We can say 1, 2, 3, doesn't look likely. 1, 2, 3, 4, 5, looking good. We can go back the way as well. 1, 2, 3, 4, 5. So there's the longest chain of carbon atoms, 5 carbon atoms. Now you could be saying, well, I can see another 5. I can go 1, 2, 3, 4, 5, like that, and kind of skip out the double bond. I'm not allowed to do that. You cannot have this carbon to carbon double bond as a branch. It's not allowed. That carbon to carbon double bond must be part of the longest chain. Even if there's a longer chain, okay? Even if there was a longer chain somewhere else, that would be fine. However, the carbon to carbon double bond needs to be part of the longest chain. That has to be part of the longest chain. So, we've found now that we've got 1, 2, 3, 4, 5 carbon atoms within this longest chain. So we know that this molecule is going to have to be pent something. There's our first step done. We've found the longest chain. Now we'll have a look at the types of bonds. We see there's a carbon to carbon double bond. It's got the general formula CnH2 CnH2n. So it must be an alkene. Put in the last 3 letters, and remember, look, I've left that gap. Why have I left the gap? To put in the number for the carbon to carbon double bond. Let's look at some numbering systems now. We could do in red, going from left to right, 1, 2, 3, 4, and 5. Or if we looked at in blue, going from right to left, 1, 2, 3, 4, and 5. Only one's correct. The one in red is correct because it gives us that carbon to carbon double bond on the smallest possible number. It's starting at carbon number 1. Whereas if we went from right to left using the blue numbers, it would be on carbon number 4 that it started on. So we're going to use the red numbers in this example. That means then that we are looking at pent dash 1 dash ene. Pent 1 ene. Ene because it's got the carbon to carbon double bond, 1 because it's starting at carbon number 1. So we have now successfully named this longest chain. Number 3, identify any branches. That looks like a branch right there. Looks like a branch to me right there. That is as we know, a methyl branch. So I'm going to put the word methyl in front of my pent 1 ene. And the last step, number the branches. Well, thankfully I've already numbered this longest chain. I've already numbered it using the carbon to carbon double bond. So I don't need to renumber it, and I shouldn't renumber it. I shouldn't renumber it as well. I've already numbered it, I'll use that numbering system. And that's very important, not to renumber the carbons, just to use the one that you've used for the carbon to carbon double bond. This branches on carbon number 2, so it's going to be 2 dash methyl pent 1-ene as our final answer here. That's a bad underline. Apologies. 2 dash methyl pent 1-ene. Right, let's look at some more examples now. So here's our second example. Looks quite complicated, but I'm sure we'll be able to handle it. We're going to go through our steps as usual. Step 1, find the longest chain of carbon atoms, which contains a carbon to carbon double bond, has to contain a carbon to carbon double bond. So let's start over here. We could have 1, 2, 3. That wouldn't work for a number of reasons. Doesn't look like it's going to be the longest chain, and also it does not contain and include this carbon to carbon double bond, so that's not going to work. 1, 2, 3, same reasons that's not going to work. 1, 2, 3, 4. There we go. There's our longest chain of carbon atoms. We could also go 1, 2, 3, 4 like that, or 1, 2, 3, 4 like that, but I always think it's easier to look at the longest chain being the middle chain. Now it's not always the middle chain, but if you can make it the middle chain, then it's quite easy to look at. So there's our longest chain. 1, 2, 3, 4 contains the carbon to carbon double bond. If we've got 4 carbons, then we know our prefix is going to be but. I need to get the last 3 letters. Is this an alkane? Is it an alkene? Is it a cycloalkane? Well, I'll look at the structure. It's not ringed, so it's not a cycloalkane. It contains a carbon to carbon double bond though, so it must be an alkene. Oops, didn't mean to do that. Must be an alkene, so it must end in E N E. I've left a space for that double bond for the numbering system. We can go 1, 2, 3, and 4, or in red we could do 1, 2, 3, and 4. Going from the bottom one, that would give us our double bond on carbon number 3, which would mean we would have but-3-ene. We already talked about that before. That doesn't exist. It's not a thing. But-3-ene doesn't exist. It must be but-1-ene, because that carbon here, this time on the right hand side, must be carbon number 1, because it allows this double bond to have the smallest possible number. So the red numbering system on this occasion is the correct numbering system, not the blue one. So let's just take out those blue numbers so we don't get confused later on. Must be the red one, because that gives us our double bond on the smallest possible number. So we have now named and identified this middle section here. We have named this longest chain with the carbon to carbon double bond as being but-1-ene. And we've also now got our correct numbering system. We don't want to change that at any point. That's the numbering system, that's what we'll stick with. Next step is identifying our branches. So we have got 1 and 2 CH3 branches. Those are both, as we should know by now, are both methyl branches. I've got 2 of them. So I write the word methyl in front of but-1-ene. Don't forget this step. I've got 1, 2 methyl branches. I must and need to write in di. Has to put that little prefix in front of the methyl, because we've got 2 methyl branches. That's what the word di means. It means 2. So we've got di methyl but-1-ene. Now we need to number these branches. We've already numbered this main chain. Do not then say, well, I want to have these branches on the smallest possible number. What you do want that to happen, but you're not allowed to just renumber this. You're not allowed to renumber this and say, well, if I renumber it, I'll get those on carbon number 2, and that'll be smaller than carbon number 3. Not allowed to do it, so don't do it. Once you've numbered it to using the double bond, stick with that numbering system for the branches. So I know it goes from right to left, and I know that this is carbon number 3. So I've got 2 methyl branches on carbon number 3, 3, 3, because there's 2 of them on carbon number 3. So there's 1, there's the second methyl branch, dash dimethyl but-1-ene. Bit of a mouthful, but if we go through this systematically, use the steps, we should be naming these correctly. Right, let's look at another example. Okay, here we go. Let's go through our steps for this example. First step, as we know, find the longest chain of carbon atoms that contains a carbon-to-carbon double bond. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, there's our longest chain, and it contains this double bond. Remember, I couldn't go 1, 2, 3, 4, 5, 6 like that. Not allowed. Must contain the double bond. So if we've got 6 carbons in our longest chain, we then know that the prefix for 6 is hex. I look at the structure, I figure out, is it an alkane, is it an alkene, a cycloalkane? It's got a carbon-to-carbon double bond, it must be an alkene, ending in E-N-E. Now I need to number. I need to number this chain, making sure that that double bond has the smallest possible number. So what we could do is if we number from left to right and go 1, 2, 3, 4, 5, 6, or we could go from right to left. If we do left to right, we see that this double bond is starting at carbon number 2, which is going to be obviously a smaller number than if we did from right to left, which would start at carbon number 4. So the green numbering system, going from left to right, is correct. It gives us that double bond as the smallest possible number. So that means we must have hex 2 ene 2 because it's starting at carbon number 2. We've identified and we have numbered and labelled this main segment here. Next step is we need to find our branches. Here is our branch. Now this is a C2H5 branch, not a methyl branch. This is a larger branch with 2 carbons. It's an ethyl branch. So we'll put the word ethyl in front of our hex 2 ene because that's the type of branch we have. And then we have a little look and see which carbon it is on. Already numbered the chain, don't renumber it. 1, 2, 3. Right, that branch, that ethyl branch this time is on carbon number 3. So it is 3 dash ethyl hex 2 ene. I don't need to put any dies or tries in front of the ethyl branch because there's only one of them. If there was 2, then I'd put die. If there was 3, I'd put try. Now then, for this example, let's work in reverse. This time we have been given the name of the compound and we would like to draw it out. Now, in order to do this, I would suggest doing this thing kind of the same way that we would write down the name if we had the structure, almost starting from the back of the word and then moving forward to the front of the word, kind of working backwards almost. Don't try and start with these branches, putting in the 2, 3 and the 5 methyl. You'll get yourself tied up in knots. Start with what we would write down first, which is the hept. Hept is the prefix for 7, so I'm going to put down 7 carbons, probably put them a little bit closer to each other, 7 carbons down in a straight chain, because that is what I know the longest chain of carbons consists of. 7 carbons in a straight chain. Then I look at the last 3 letters. Right, it's an alkane. It ends in E-N-E. It must contain a carbon-to-carbon double bond. Where is the double bond? Well, that's what that number means. It tells me that the carbon-to-carbon double bond starts at carbon number 1. Let's make carbon number 1 on this carbon here on the left hand side. We could also put it over here and that could be carbon number 1. That's totally fine, but I think it's easier, or at least I find it easier, starting with this being carbon to carbon, being carbon number 1. So we now have our longest chain completed, and I'll put the other bonds in between the carbons. Now I can move on to my branches. I've got methyl branches. How many? Try means I've got 3 methyl branches. Great. The positioning of those methyl branches, here they are here. There's 1 on carbon number 2, 1 on carbon number 3, and 1 on carbon number 4. But we've already decided that this is carbon 1, so that must be 2, 3, sorry, did I say 4? I mean 5. Carbon 4, 5, 6, and 7. First one will pop in on carbon number 2, methyl branches are CH3 branches, 1 carbon, 3 hydrogens. There's also another one on carbon number 3. I'll make this one sticking down the way just to give myself a little bit more room. And then the last one is on carbon number 5, like so. And now all that's left to do is to go in and put down the other hydrogens and bonds within this molecule. I'll just get rid of these numbers, make it look a little bit neater. So we know that every carbon makes 4 bonds. This one has 2 bonds already, so I'll put in another 2 hydrogens. Second carbon already has 1, 2, 3, 4 bonds. Okay, great, that's done. Third carbon has 1, 2, 3, so it just needs 1 more. Fourth has 2, it needs 2 more. Fifth has 1, 2, 3, needs 1 more, and then so on and so forth, with the last one needing 3. And that's us. There we go. We have drawn out what seemed to be a pretty complicated name, 2,3,5-trimethyl heptone, but if we go through our steps, hopefully it wasn't too bad.